started, and what can you do with it today and what can you do with it in the near future, right? So that's what this talk is about. And so I'll before the slides come up, right, so I'll tell you, so what is so special about quantum computers that it has generated so much interest? Any thoughts? Yes, go ahead, please.
Either 0 or 1, they can exist in somewhat of a superposition of between two states.
Yes, yes. So on your classical computer, on your phone, for example, the basic information unit is the bit. And what is the bit? Bit is 0 or 1. So anything you do on your phone or any program you write is based on the underlying information unit that your computer uses is the bit. And as this person said, in a quantum computer, what is special is your basic information bit, which is a qubit, quantum bit, can be both 0 and 1 simultaneously. So it is like you toss a coin, when it is in the air, is it head or tail? It is both. Okay? So in the same way, your qubit can be both 0 and 1 until you observe it. Just like the coin, until you take it in your hand and you say, okay, I am seeing, okay, it's head. Until you do that, it can be in both heads and tails state. The other thing you also mentioned is that I have a qubit, you have a qubit. I am tossing my qubit, which can be both heads and tails. You are also tossing your qubit, which can be both heads or tails. If they are entangled, then by looking at my coin, I can say what your coin did. That is called entanglement. Now, how many people have heard about Einstein? Of course, everybody has. So, do you know what Einstein thought about quantum mechanics? Yes, again, go ahead. Sorry?
God doesn't roll dice.
Yes, exactly. So Einstein said that God does not play dice with the universe, so quantum mechanics does not exist. It's just that we don't know enough mathematics today, 1920s and 30s, that we don't know enough mathematics. Someday somebody is going to do, come back and say that, okay, quantum mechanics can be explained. There is more maths to it. And that day we will see that, it's not probabilistic, but it is deterministic. Okay, so that's what he said, right? And the exact words that he used were, God does not play dice with the universe. Then in 1935, he also wrote a paper where he said that this property of entanglement, what is the property of entanglement? Two people toss the coin. If they are entangled, looking at one coin, you know what the other did. And it doesn't matter where that coin is. I can be here, you can be here, or I can be here and you can be at the other end of the universe. It doesn't matter. They can still be entangled. And to this, Einstein, I forget the exact words, but yes, go ahead.
Spooky action at a distance.
Yes, spooky action at a distance. So 1935, he wrote a paper, a research paper, which said entanglement does not exist. It is spooky action at a distance, and one day we will know enough maths to disprove entanglement. Okay, then come to 2022. 2022, what was the Nobel Prize in Physics for? It was for disproving Einstein. Einstein 1935 said spooky action at a distance, and 2022, 4 people got the Nobel Prize, and it was for disproving Einstein and proving that entanglement is possible. Okay. So, using superposition, entanglement and these qubits, you are now building computers. Okay. So, that is what a quantum computer is. Now, so we will look at some things that you can do with quantum computers. One example, in the air there is nitrogen, right, lots of nitrogen, about 80% of the air is nitrogen. In the soil there is no nitrogen. So, what do? We make fertilizers, take the nitrogen in the air and put it into the soil. What is the population of Earth? 8 billion. If we did not have fertilizers, how much food can we grow? We can grow only food for 4 billion people. The remaining 4 are supported by fertilizers. Now, fertilizers making is one of the most polluting industries that we have. We cannot stop making fertilizers because if we stop, half the population cannot eat on Earth. But we need to make fertilizers, but fertilizers today are one of the most carbon producing industries in the world. Okay, so it produces lot of carbon dioxide. Similarly, we all drive cars. That catalytic converter in your car produces a lot of carbon dioxide. Financial models, we know there were these financial bubbles that got burst in 2008, and it keeps happening, right? Every 6 months RBI says, I am going to increase the interest rate, I am going to reduce the interest rate. How does it come up with that number? Today it comes up with that number through experts sitting in a room and saying, okay, I think 0.25% is the right one because inflation is here, our money flow is this much, as a result I think it should be this much. And then the RBI governor says, okay, I think 0.25% we should increase the interest rates. But there are other better ways of doing it. If you could, there are better ways of doing it. You could simulate saying that at 0.25 what happens, at 0.5 what happens, at 1% what happens, right? And we all know COVID. What happened in COVID? We quickly came up with some vaccines, but how do we do it in a more effective way? And that's where quantum comes in. Quantum computers use qubits which are subatomic particles. So that qubit which I talked about in a quantum computer is actually a subatomic particle. Okay, so you make quantum computers using photons, neutrons, electrons, the subatomic particles which are there in nature. And all of these processes also involve subatomic particles, okay, and that's why you are able to, yes, go ahead, sorry.
There are more subatomic particles like muon, tau, so
yeah, there are. We don't use them today, but maybe you will grow up to teach us how to use it. But right now it is neutrons, electrons, those bigger particles. The ones you are talking about are the very, very tiny ones, right? So now this used to be the most fastest supercomputer. Now it's the 4th fastest. We have already reached exascale computing, which means in a second you are able to you're able to do so much computation today, but there are still a lot of things that you can't do with it. Coffee, okay, coffee molecule is one of the small molecules, okay. It's one of the small molecules in nature. What are bigger molecules? The carbon, yes? Sorry? Hot sauce. Yes, I guess it has a bigger molecule. I don't know, okay, so, but caffeine is one of the smaller molecules. Now, if you were to try and simulate caffeine on a classical computer, how big do you think that computer needs to be? That computer will need 10 to the power 48 bits. 10 to the power 48 is how much? 1/10 the number of atoms present on Earth. Will we ever build a supercomputer that big? We'll never ever in the future of humanity, we will never build a supercomputer that big, having so many bits, okay? And that's where the quantum computer comes in, because in a quantum computer, using just 160 logical qubits, you will be able to simulate the molecule of caffeine. Now, why is it very important to simulate molecules? So, today, how do you make drugs? So, we know about COVID, people had to make medicines. Today, to make a medicine, you say that, okay, there are these 100 molecules that I know of, okay. Historically, I have seen that this molecule is typically good in a medicine. So, what I do today is I take a molecule, I take a disease, I pour them, and I figure out which molecule works best as a medicine. That's how medicines are made. After I figure out the molecule, I then go to AIIMS and I say, give me 50 people, 25 of them who have the disease and 25 who don't have the disease. I will give them all that medicine, and I will look for side effects, I will see whether it is effective. All of those things I do, and that's why drug discovery today takes 5 to 10 years. Okay. Making a new medicine today takes 5 to 10 years. We accelerated it during COVID time for the vaccines and other things. But we also know that a lot of people got a lot of side effects due to vaccines from COVID time, right? And that is because, it did not go through the regular test process at AIIMS and other places. If you see, the current vaccines are not called actual drugs. I think they're called beta drugs or whatever, right? I don't know what the right name is. But they're not yet fully passed, okay? They're not fully passed. And so drugs take 10 years. And if you are able to use a quantum computer, what it means is you will not have to do that thing in your test tube. You can actually try and simulate what is happening inside your test tube, okay? You don't have to go and pour it and observe, but you can actually simulate it on a quantum computer. So that's the advantage of a quantum computer. And quantum computers today are for things like, okay, we'll come to that. So, but before that, so for the first time in the history of computing, you now have two types of computers, okay. Up to now, there was only one type of computer, which was based on the bits. And based on that, you built your mobile phones, you built your laptops, you built your supercomputers. And today, for the first time, there is a branching happening, okay. There are two types of computers that humanity today has. One is the classical computer, which we have all been so used to, and the second is the quantum computer that has just come in now, right? And we already discussed, this one uses bits, zeros and ones, and the other one uses qubits, which is zeros and ones and everything in between, okay, everything is possible. And this is a roadmap. How many people have heard of Moore's law? Okay, somebody who can tell us what is Moore's law? Okay, Moore's law, very simply stated, says that every 2 years, the power of my computer is going to double. Okay, it doubles. That's why over the past many years, you have been seeing every year a new iPhone comes. Why? Because that has doubled, almost doubled in power. So it is doing better camera, better apps for you, more power, more storage, all those things. Why? Because Moore's law has been saying that everything doubles in 2 years. But remember, exponential laws are not perpetual. They will stop at some time. Okay. Moore's law hasn't stopped yet. It is still going strong. So maybe for the next 10, 15 years, we don't have to worry about it, maybe. But Moore's law is doubling. In the same way, quantum computers have been doubling every year. Unlike Moore's law, which is every 2 years, quantum computers so far have been doubling every year. So, which means that, you know, the youngsters here, by the time you graduate, quantum computers are going to have commonplace. Okay. In fact, they already are. I'll tell you how they are common, but we'll come there. So this is just saying that in 2016 there were 5 qubits, and come to 2024 there is 133, and there is also 1,000 qubit, and by 2033 we will have 100,000, 1 lakh will be touched. Okay. So it is growing exponentially, and yes. So coming to the first question, can you access a quantum computer? Yes, you can. Since 2016, quantum computers are available on the cloud. Okay. And you can actually sit here, just type IBM Quantum, just like you create a Gmail account, you can go and create a quantum account, and you can start programming a quantum computer. And even if you don't know programming, there is a visual composer there where you can just drag and drop gates and things and build a program, okay, to solve your problem, right? So if you're a programmer, great. If you're not a programmer, still great, because you can still build something out of it, right? And since that day in 2016, there are about 500,000, 5 lakh users plus many things. And I asked you the question, where are the maximum number of software or quantum engineers present? It is in India. It is in India. Out of those 5 lakh users, about 1/4 to 1/5 are from India. Okay. So lot of Indians today are already users of quantum computers, and they are beginning to solve some of the problems which I talked about, right? So what are quantum computers good at? Will they replace our classical computers? No, they will not replace your computer, because our classical computers are very good at many things, you know, like your mobile phone. It's great at several things. You don't have to replace it. But it will come in where it is simulating nature, because like I said, the qubit works exactly like nature, just like the things in the test tube. It is working just like that, right? So when, for example, ISRO wants to build a new material for its next Gaganyaan project, how does it do it today? For a rocket, what is important? It needs to be very, very strong. It needs to withstand heat, because as you push up the rocket, huge temperatures there. But it needs to be very light. Why? Because the lighter it is, the less fuel it requires, right? And the cheaper your mission becomes, right? So for all these things, and the same applies to your car also. Maruti is always looking for new materials for its body, chassis. Over the past 5 to 10 years, I don't know if you have observed, but the body of the car has completely changed from tin or iron or whatever to now polyfibers. Okay. So in fact, the body of the current cars are not metallic. Many of them are not made of metal today. But they're as strong as those earlier materials, and they are lighter. So which means your car becomes more fuel efficient, right? So to do all of that, you're trying to simulate nature. AI, we all know about AI. So we've been talking about LLMs, right? Do you know what is the biggest concern about LLMs today? The biggest concern today, yes? Yes, computing power and the carbon footprint is the biggest concern. in US, there have been new power plants, coal power plants, which have come up just to support the new LLMs. Okay, so Google builds a new LLM and all of us are very happy, but at the back of that is a power plant sitting there producing carbon, right? And there are now projections saying that as we as we try and raise the accuracy of our LLMs, it is going to reach a point where the amount of power requirement is going to scale exponentially, okay? Which means that it will no longer be sustainable. So many people are talking about sustainable computing, and that concern is coming from how do you run these AI models more efficiently, so that the efficiency can be in two things. It can be either new hardware, which could be quantum, or it could be new algorithms. So currently we have the transformer models which are running the LLMs, but there could be better algorithms, right? So both of those are things. Okay, so where are these quantum computers today used? Okay, so quantum computers today are used in healthcare, in oil exploration. Boeing is using it. One of the biggest problems when it comes to aircraft, cars, oil rigs is corrosion, rust. It's the biggest problem for aircraft, for example. So Boeing wants to find, how do you find better materials which are rust, they don't rust, or you can paint them so that the rust becomes lesser. Okay, I'll skip all of this. Yeah, so let's just one example I'll give you from. Yeah, okay, this is from IIT Madras. So we all know about UPI, right? We all make our transactions using our mobile phones and all of that. Now, do you know how many fraud transactions happen on UPI? It's about 0.1%. Okay, it's a small number, but among billions of transactions, it's a large number, right? And also the big problem with fraud is that, so there is this thing in New York subways. There have been 4 or 5 cases of people pushing somebody in front of the train. Okay, how many people go in the train every day? Millions. In a month, millions of people go. Only 6 where people have pushed in front of the train. But you know what it does to all our psyche, right? We all become scared. We don't want to go to the metro. So that's happening in New York now, right? Because there are these crazy people who come and push you in front of a train. It's 0.001% of number of people who use the train, but it still plays on your mind, and it reduces the confidence or the trust that you have in the metro system. So in the same way, UPI also, you don't want that number of fraud to go up, because if it does, today we are all using it, but then if it crosses a certain threshold, then we all start to fear. We say, okay, this doesn't look safe for me. So one of the problems that IIT Madras is trying to solve is, how do you find these fraud cases, right? So for example, if I have to teach what is a cat to my daughter when she was 2 or 3, whatever, how many cats do you think I had to show her before she said that's a cat? 1. Do you know how many cats I have to show to an AI model for it to understand that this is a cat? Yeah, it's thousands. I have to show it a black cat, white cat, brown cat, cat with half its face covered, cat from behind, cat from side, all these different cats I have to give it, okay? So I have to give it 10,000 cats before it knows it's a cat, whereas my daughter learnt it with one cat. Quantum is somewhere in between. It doesn't need 10,000, it can't do it with one, but it's tending towards humans, okay. So that's why the power of quantum is immense, and that's why you want to use it in things like this, where you're in UPI transactions, where it requires fewer cases, but it also generalizes better. So we heard about artificial general intelligence. To reach there, we certainly can't do it with our current computers, our deep learning models, because they require exponential power and processing power. So I'll sort of, the other thing that quantum is very, people are afraid of is all our transactions today. Do you know what our transactions are based on? Cryptography, what is it based on? Yes, somebody here? Yes? Public key, yeah. Do you know what is the basis for public key encryption? Yes.
Like if you have to factorize two very big prime
Yes.
numbers.
So encryption is based on the fact that what is the prime factors of 15? 3 into 5. What is the prime factor of 49? 7 into 7. What is the prime factor of 9, 3, 7, 2, 1, 9? A big number. It will not, the best supercomputer will take billions of years to factorize a large 2048-bit number, right? And that's the basis for all our transactions today. Online transactions are based on the fact that you cannot factorize large numbers quickly on any supercomputer which is there. But on a quantum computer, you can do this within a few minutes, and hence people are now switching to new quantum safe encryption techniques. In fact, there is fear, for example, from the Indian government that China is just collecting our data, just not decrypting it, just keeping it, and then once the quantum computer is there, they will just break it, right? Break the encryption. Because government secrets, defense secrets are not for 1 or 2 years, they are for 10 years, 20 years. The Bose files, we have still not, it's still not public, right? So, so with that I'll stop. The only thing I want to just say is that, okay, I already told you India is the place for quantum computers, and India has started what is called the National Quantum Mission, okay. 6,000 crores, the government has said that India has to be the quantum power of the world in future, okay, and they have started investing money into this, and starting this year, they are actually putting in money into quantum computers. So we became a software nation, we all know that, but we missed the bus on hardware, we missed the bus on semiconductors, but in quantum, the government wants that we should do well in quantum software, quantum hardware, and quantum semiconductors, all the three. Okay, and that's why this national mission, so that youngsters like these, in future, India will become a computing power which has all facets of computing with it. Okay, so I'll stop there. Thank you.
Thank you. Thank you, Venkat. Any other questions for this? Yes, sure.
Hi, thank you so much, Venkat, for such an enlightening session. My name is Jean. I'm from IBM. I'm the learning lead in IBM, and I closely work with Venkat to deliver some of the training programs for quantum. And we did a fantastic one in by the year end of 2022. It was such a big hit. I mean, there were like 50 quadratic equations on a slide. Nobody understood anything, but the learning program had an NPS of 100. And come 2023, we had this Gen AI spurt, which totally disrupted all our learning. So to bring back the focus, what is quantum with the Gen AI boost? How is it going to look for us? What can I teach my next set of folks in the talent pyramid so that they can upskill fast?
Yeah. So see, Gen AI is today's technology, right? Where it's already made a huge impact. All of us have moved to OpenAI. I mean, the ChatGPT platforms and all. In IBM, I will tell you, HR has been replaced by HR GPT. Support has been replaced by Support GPT. Marketing has been replaced by Marketing GPT. Thousands of people gone, GPTs are in, right? So it has made an impact already. I mean, both positive and negative, right? All the coders today are 2x more, quicker because of copilots and stuff, right? But when will quantum start impacting this? Not yet, okay? It's not there yet. Right now, it is still in small molecules. It is still doing small, machine learning tasks. You cannot build a LLM, for example. You can't build deep learning models with this. It will get there in the next 5 to 10 years. That's the expectation, okay? So, I graduated in 1991 with my BTech. At that time, nobody came to colleges to hire anybody, okay? We just sat there and hoped that we will one day find a job. We all learnt BASIC and Fortran, but there were no computers to program. There were no jobs, okay? But come to 1997, 1998, and India, because of people like me who were sitting idle without any, who knew programming but who did not have any jobs, suddenly India was, the place from where you can get talent to go solve the problems of the world, and that has continued till today, right? So quantum is in that 1991 stage. You can learn it and get ready in this decade. It is going to happen, okay? So in this decade, quantum is going to be there. By the turn of the decade, you will see a lot of, in fact, hiring is already happening in India, okay? Thousands of people, well, not thousands, but hundreds of people have gotten hired.
Sir, my question is similar, that we use quantum qubits. There is lots of correction bits currently. Last time I heard for each qubit, there were like millions of correction qubits to give the correct answer. So when do you think we will have an sustainable amounts of correction qubits? And what is the current state? How many correction qubits are required for each qubit?
Yeah. Okay. So the very important question which we did not go into, a bit, once you put it in 0 and 1, it remains there forever. Okay, you put it at 0, it is forever in 0. But a qubit remains in its current state for how long? For milliseconds. So within those milliseconds, you have to do your computation. Okay, and they are also noisy, as he pointed out, right? Which means that today's quantum computers are noisy, and they give you a very small window of computation. So you have to do it in milliseconds, okay? So to answer that question, again, the turn of this decade, there is something called quantum advantage. What is quantum advantage? Any problem that you have today, if you can solve it much, much faster, much, much cheaper using a quantum computer, that's called quantum advantage. Have we reached there yet? Yes, mathematically we have reached, but we don't have quantum computers which show that quantum advantage yet, okay? So when are we going to show that? IBM says in the next 2 years. There are some startups also which are saying next 2 years. So next 2 years are going to be very exciting when you'll start seeing applications where people will show that, noise does not matter, coherence time does not matter, and I can solve a problem which classical will never be able to solve. Okay, thanks. Yeah. Okay.
Thank you. Thank you again, sir, for a really informative session, and especially overwhelming to kids to answer all the questions which we couldn't. So I would like to invite Pranshu Gupta to hand over a token of appreciation to L. Venkat Subramaniam. Yes. Can we keep applauding, please? Because it was really informative and really